Welcome, everybody. This is the IROS 2021 workshop on Safe Real-World Robot Autonomy. With this workshop, we aim to initiate an interdisciplinary exchange on the development of safe real-world robotic systems. My name is Angela Schöllig. I'm an associate professor at the University of Toronto and a faculty member of the Vector Institute. I've been organizing this workshop with an amazing team of colleagues and students, so let me show you their faces. So Animesh Garg is an assistant professor at the University of Toronto, a faculty member at the Vector Institute, and a senior research scientist at NVIDIA. So he has been one of the co-organizers together with Somil Bansal. He is an assistant professor at the University of Southern California. And before joining USC, he spent a year at Waymo working on self-driving. The majority of the work behind the scenes was done by SiQi Zhou, Melissa Greeff, and Lucas Brunke. They are all PhD students in my group who have been working on learning-based approaches for robotics and have demonstrated their work on indoor and outdoor aerial vehicles. Melissa and SiQi are also in their final year of their PhD, so watch out for them. Finally, Adam Hall and Justin Yuan, they are also grad students in my group working on machine learning for robotics, are helping out during today's live session. So yeah, so now that you know all the faces of the organizers, let me go back and introduce the topic. So what motivated us to organize this workshop? We envision robots to play an increasingly important role in our lives. This includes applications in transportation, monitoring, health, and robots are also envisioned to become our co-workers at work, but also at home. And when deploying robots in the real world, safety of operation is an essential requirement. Robot safety has been reasonably well characterized in environments such as warehouses, factory floors, or in the air. Basically anywhere where the dynamics of the robots and their environment are relatively well understood. However, we expect the next generation of robots to perform complex tasks in unstructured and dynamic environments, such as, on our roads, but also in our homes where, we have complicated setups, that need to be cleaned up. And this requires robots to act safely despite the uncertainties in the environment. So the first challenge for robot safety in these new applications is that we deal with unstructured, dynamic, and uncertain environments. The second main challenge is that we increasingly rely on machine learning algorithms in robotics overall to achieve these complex tasks. And machine learning is used not only in one of the components, but usually in all of the components in a robotic system, from perception to estimation to planning and control. And these components may even interact with each other. And we all know that safety and robustness considerations for machine learning algorithms are still relatively rare. So in this workshop, we bring together researchers from academia and industry to discuss safe autonomy for real-world robotics applications. And we focus on three key areas. The first one is safety definitions and requirements. So how do we define safety? And what are the safety requirements for these next generation of robots? The second one is open challenges and opportunities. So what are the open challenges and opportunities for integrating theoretic and data-driven approaches in this context? And the third area is benchmarks and evaluations. How do we evaluate safety of their algorithms? And do we need new benchmarks focusing on evaluating their safety before we deploy them in the real world? In short, with the continuously advancing capabilities of robots comes also higher demands for safety. And how do we address these demands? The structure of the workshop is as follows. We have 3 panels, 35 minutes each, one on safety definitions and requirements for real-world robotics applications, one on the challenges and opportunities, and the third one on benchmarks and performance metrics for safe robot autonomy. We have amazing panelists for all 3 of these panels. And if you want to still hang out with us after the concluding remarks, we have a post-workshop social till 1 p.m. Eastern time, and we would love to see you there. To tell you a bit more about the panel structure, each panel starts with a 2-minute introduction of the panelists and the topic. Then each panelist has 1 to 2 minutes for an opening statement. And afterwards, we have a moderated discussion where we will also include your questions. And so you can add your questions to our question board anytime. And you find the link on our workshop webpage, which is tiny.cc/IROS-safe-robotics. And you can also upvote questions others have posted or comment on them. So yeah, please use that way to interact with us and interact with the panelists. This will definitely enrich the discussion. So in addition to this live component, we have several offline components. And we really encourage you to look at them after the workshop if you haven't done so. The first one is we have 8 outstanding invited spotlight talks that highlight recent research on safe and certifiable machine learning for robotics. And they fall into the 3 categories of our panels and are 5 minutes each. So please go ahead and watch them. They are also featured on our webpage. A second component is our review paper on safe learning in robotics. And you can find a preprint version of the paper on archive. And there will also be a tutorial video published shortly on the workshop webpage. I'd also like to briefly point out that my group has done a recent effort to establish a safe learning benchmark called Safe Control Gym. So if you're interested, the archive version is also available and you find the code on GitHub. So finally, before we start the first panel, I just want to kind of give you all the important information that you need throughout the workshop. And then we go right into the first panel. So you see here at the top, again, the page of our workshop. We have a post-workshop event, and that event is also linked on our workshop webpage. The important thing to note is that it requires a password that we don't share publicly. So please make a note, the password is IROS 2021. We also have an upcoming NeurIPS workshop on a related topic. The topic is deployable decision-making. And the deadline for an abstract submission is October 8th. So please consider participating and submitting your work if you are interested to join. We have also summarized all my group's activities on the topic of safe robot learning on the webpage saferobotlearning.org. This webpage also features the IROS workshop and the NeurIPS workshop. And on this webpage, you also find a form where you can sign up to our mailing list and get all the updates about upcoming events. Finally, we have also been organizing invited sessions on learning-based control at CDC for the past few years. And the next one is happening in December of this year. So this is all the information. Now, without further ado, I hand it over to Somil to moderate our first panel. Thank you all for joining.
Thank you, Angela. And hello, everyone. Welcome to the first panel discussion of the workshop. I'm Somil Bansal, and SiQi and I will be the moderators for this panel discussion. This panel discussion in particular will focus on understanding the safety definitions and safety requirements for real-world autonomous systems. In particular, how can we even define the safety for real-world systems, and what are the key challenges in doing so? And it is my immense pleasure to introduce our panelists today. Our first panelist is Professor Naira Hovakimyan. Naira is a professor in the Department of Mechanical Science and Engineering at UIUC. Naira is broadly interested in the intersection of control, optimization, machine learning, robotics, and autonomy. Her work on adaptive control has been used on real aircrafts for ensuring safe flights. Welcome, Naira. Our next panelist is Ryan Gariepy. Ryan is the CTO of ClearPath Robotics and Automotors. He also serves on the board of directors for the NSERC Canadian Robotics Network, the Open Source Robotics Foundation, and is also co-founder of ROSCOM, the first and the largest conference for robotic developers. Ryan regularly speaks on topics from technology-focused lectures at major universities, at UN. Also, he has given several live interviews on the topic with CNN, BBC, and CBC. We are very excited to have you, Ryan, on the panel today. Welcome. Our next panelist is Professor Marco Pavone. Marco is an associate professor of aeronautics and astronautics at Stanford University, where he's the director of the Autonomous Systems Lab and co-director of the Center for Automotive Research at Stanford. Marco is also the director of autonomous vehicles research at NVIDIA. His research interests are in the development of methodologies for the analysis, design, and control of autonomous systems. It is a great pleasure to have Marco join us on the panel today. Welcome, Marco. Our last panelist for today is a good friend and colleague, Felix Berkenkamp. Felix is a research scientist at Bosch Center for AI. Before Bosch, Felix completed his PhD at ETH Zurich, where he received the Alice PhD award for his dissertation. Felix is broadly interested in enabling dynamic systems to safely and autonomously learn in uncertain and real-world environments. We are very excited to have you here, Felix. Welcome. So the plan for the rest of the panel will be that we will start with the opening statements from our panelists. It will be wonderful if panelists can keep it between 1 to 2 minutes. So we'll start with Naira, then Ryan, and then Marco, and finally Felix. Naira.
Muted, sorry. Good morning, and thank you for having me for this panel. Thanks, Angela and Somil, for putting together this very important topic. And as an introduction, I would just repeat that I have worked 25, 30 years in the area of optimal control, differential games, optimization, robust control with applications and technology transitions to aircraft control systems. And with the recent explosion of data-driven methods, we have transitioned to robotics applications, working in safe learning methods, bringing machine learning and control together to impact robotic applications. That's the brief introduction on my background.
Thank you, Naira. Ryan?
Of course, thank you very much. So just in terms of the topic at hand, thank you for inviting me. And when it comes to how we look at safety ourselves with our vehicles that are in the field, we have millions of hours autonomously, millions of autonomous hours operating already in the field with no safety incidents. That's courtesy of, that we're working in the manufacturing and warehousing field, which is much more mature from a standards body perspective. And to us, what safety really means is preventing people from being harmed, whether that's directly by the robot or indirectly by some sort of first or second order results, like a robot knocking over racking and what have you. However, we still have a bunch of challenges, even though there are quite a few standards for us to work within, particularly defining what expectations we have of humans that can be transposed to a robot system. For example, it's generally understood and codified that robots need to be better than the average worker at avoiding collisions. However, there are a lot of corner cases which haven't been defined. For example, if there's a forklift driver who hits someone in a trailer while the forklift driver is unloading that trailer, they're generally not considered to be at fault. However, a robot doing so would be at fault. And that's the sort of thing that can cause some headwinds to adoption. In terms of some of the other discussion points, absolutely, we need to think about guarantees. For us, there's always a guarantee that, each robot hour of operation has a 6 to 7 nines likelihood of being completed without causing severe injuries. That's kind of a simplification of performance level D in a certain ISO standard. Beyond that, there's always a trade-off, but when it comes down to it, we always need to guarantee some base level of safety. As for where the safety community needs to focus on, frankly, I think I'm a little bit contrarian here, that I think that for 95% of companies or organizations or labs, we need to focus on environments where the regulatory and risk assessment guidelines are established and realistic. So assuming that your system requires functional safety as opposed to intrinsic safety, this means avoiding the general public. The reason for that is that environments with the general public really don't have good risk assessments done. For example, if you did a risk assessment on human-driven vehicles in human-driven environments, such as we all generally interact with all day, that risk assessment would probably say that the entirety of the public road network needs to be shut down immediately. So it's kind of counters. It's another headwind to adopting robots and autonomous systems. However, there are many companies who are growing in maturity there. So I think there's a big open question that we should also look at regarding, in particular, how simulation and analog testing should or shouldn't count towards considering a system well tried. For those of you who know, well tried systems do kind of count towards safety if you can rack up enough hours safely. And then, to touch on the final point here, is it even possible to define the safety for today's real-world robotics systems? Well, absolutely. In many cases, the safety for real-world robotic systems is defined traditionally in systems like aircraft, particularly robotic aircraft. The key is going to be building on foundations we already have, whether it's in the industries themselves or in lateral moves of technology that was developed for one industry that can then be considered well tried within that industry and moved into a peripheral application. So thank you very much for your time, and I look forward to the inevitable discussion.
Thank you, Ryan. Michael?
Yes, well, first of all, I'm very happy to be part of this workshop, which is very timely. I think that all the questions on your website are excellent, but the one that I was really intrigued by is whether current safety standards, such as those in the aerospace industry, are enough for highly autonomous systems. And my answer will be only in part. So first of all, traditional safety, in particular in the automotive sector, as also Ryan mentioned, is meant as a functional safety, where the focus is to avoid accidents due to malfunctions of system components. And this is, of course, absolutely needed. But for highly autonomous systems, an equally important notion of safety is the notion of safety of the intended functionality, where one reasons about accidents that happen even when all the components are functioning properly. For example, due to a lack of situational awareness. So this is a notion that needs to be added, in my mind, in my opinion, to existing notions of more traditional notions of safety from the aerospace industry. Second, again, particularly for highly autonomous systems, is typically not very clear how to translate component level specifications into system level safety specifications. And finally, and this is again related to some of the points that Ryan made before, is defining safety metrics for real systems is actually challenging. Oftentimes we mean safety in terms of avoiding collisions, but in reality, we also want to reason about the consequences of such collisions. For example, a front crash is much worse than, say, a crash on the side. And also one needs to reason about a more nuanced aspect of safety. For example, by taking into account notions of responsibility or context dependency in order to avoid conservatism and somehow strike a good balance between safety and risk. But how to build in such notion of responsibility and context awareness is really an open research topic.
Thank you, Marco. Felix?
All right, first up, also thanks a lot for having me. So as Somil mentioned, I recently at this point 2 years ago, switched from academia to a more research-oriented role in industry. And so the one thing that I found striking during that kind of transition is kind of the disconnect between some of the research that happens and kind of the applicability directly to the real world. And so in particular, if I look at kind of real world systems, it's usually like there's a vague definition of safety, but this safety typically is defined with respect to some model. And we don't usually have like really accurate models that model all these interactions with the environments. So that's kind of the first point where you suddenly start hitting issues. And in addition, like a lot of real world systems are actually partially observable. So POMDPs, where a lot of the theory that recently has been developed doesn't directly apply to kind of certify safety of these systems in connection with machine learning. So kind of all of these things together kind of open like a really interesting and broad research space kind of for methods that on the one hand kind of can rely on poor models, but on the other hand, you always actually need some real interaction on the real system, some real world data in order to actually make ultimately statements about safety. And I'm really kind of looking forward to discuss all of these topics with the other panelists.
Thank you, Felix. In fact, I will maybe start with I'll start with you because you raise a very good point here. So you said like in real world systems, I mean, the models are not available, the environment is partially observable. During your PhD, you have thought a lot about sort of thinking about theoretical safety guarantees. Do you think that perspective has changed in any way at Bosch? Do you still think in terms of theoretical guarantees, or your notion of safety had changed? And if so, what was the biggest reason for that?
So I think ultimately theoretical guarantees are still desirable because, I mean, as also Ryan and Marco mentioned, but like in real world systems, we do need to eventually give some guarantee, right? We are going to deploy these systems in the real world, and it's not really possible to do that unless you have some at least notion of safety and you have some kind of confidence that this system is actually going to work. I think the really tricky part is this part where kind of in theory you can say, okay, I just make this assumption that this is a POMDP and maybe my noise has kind of certain properties, right? And then I'm going to learn a model, and then I know this model is going to be close to perfect, right? It's going to accurately represent the real world. And I think that's kind of where kind of the disconnect happens, because that doesn't actually happen in the real world, right? Like the real world is a really messy place, right? It's partially observed, right? So you're kind of all the guarantees where the statistics community is currently at, where we can provide guarantees, typically don't hold in the setting. Then inevitably something will go wrong, and you're kind of during the learning process, kind of your model will not be kind of a real representation of the world anymore. And at that point, all your safety guarantees kind of go out of the window. So I think, so for me, the biggest change hasn't been so much in kind of how to think about safety. Kind of it's still, I still think like kind of robustness and safety constraints, all of these have real meaning in the real world. I think the problem lies in kind of the assumptions that we make to actually provide guarantees in the real world, right? Like there's a theory side where you can actually show stuff, and then there's kind of the real world, which is messy, and you actually need to kind of interact with the systems, and you kind of can't just rely on the models. There needs to be some kind of data component that you exploit, because the model is never going to capture everything.
That makes sense. I'm going to come back to that point, but before that, I have a question for Marco. So Marco, you have been thinking about safety metrics in academia for a long time now, and now you are directing autonomous vehicle research at NVIDIA. What do you think about sort of defining safety metrics for autonomous cars? Like, do you think we can even define a safety metric or a single safety metric for autonomous vehicles? If so, what do you think those metrics should be?
That's actually the point that I was raising before. Coming up with good definition of safety is much harder than people might think. As I said, the trivial way to do it would be to say, I want to avoid collisions at all costs. But then, especially when a robotic vehicle interacts with humans, one also has to reason about the notion of responsibility. If someone on the highway so if your robotic vehicle on the highway slams on the brakes, is that an unsafe behavior or not? Well, it depends. If someone in front of you also slammed on the brakes, then it's reasonable. but otherwise is actually unsafe and unreasonable behavior. But how to formalize this concept as well, the context awareness concept, into something that is quantitative that you can use for evaluation and optimization is very challenging. So if anything, my experience at NVIDIA is really teaching me how the notion of safety is multidimensional, and even defining such a notion is still very much an open research problem. Very quick comment about what Felix was saying. I agree largely with what he mentioned. And this is the reason why oftentimes I do not like to talk about guarantees, but more about assurances, in the sense that we do need those theoretical statements, but not because they give us absolute truth that the system is going to work, but more because they are a driving function to design algorithms that have more solid foundations and hopefully more robust in the real world. So I see guarantees more as a driving force to design better algorithms, as opposed to just absolute truth that we should strive for.
So when you think about assurances, like what sort of extra pieces in the puzzle that we are missing right now in terms of like tools that people focus on in the safety domain right now? What are the tools that we are missing for getting to like assurances for, say, something like autonomous cars?
Well, I think that half an hour will not be sufficient to overview all the tools that we're missing. Certainly in terms of evaluation, this is actually a topic that is not addressed much in the academic world, but it's extremely important in the industry world. How to collect the data and how to properly sample and stress test your system in order to find corner cases is a big open question. But then the other important topic is how to combine all the component level safety assurances or guarantees into something that is a system level. Unfortunately, in every component of the autonomy stack, people necessarily introduce hacks, and the hacks compound. And then what you get at the end is something that oftentimes is very difficult to reason about. And that's why you really need a evaluation that somehow provides insights in how your very hacky thing works together.
That makes sense, Marco. Thank you. And my next question is to Ryan, because it sort of connects to Marco's point. So Marco raised this situational awareness aspect to the safety of autonomous cars. And Ryan, in your opening statement, you also talked a little bit about the importance of perceived safety. Maybe I'm just giving it a name, but you were giving the example of this forklift driver, where a human doing the same task may perceive to be safe, but if the robot is doing that, we think about it as an unsafe behavior. So for robotics, where do you think this balance lies between perceived safety, which is become important when the robots sort of when we think about real world applications, and safety guarantees, which is typically thought about in like controlled environments as like aircrafts, for instance. So where does that balance lie in your experience?
Well, the balance changes. The balance changes basically every month, every day that robots or increased technologies in the field, right? Like it's the same argument that says if you could wave your hand and replace every car in North America with autonomous cars, and you only killed 5,000 people a year with those autonomous cars, is this okay? Like, from a rational perspective, from a utilitarian perspective, it's an improvement. But it would probably not be really accepted if you did that right now. But on the other hand, we know from history, again, looking at the automotive field, that people didn't used to trust cruise control either, right? And now people generally trust adaptive cruise control extremely well, right? And now we're having these debates about autonomous cars. I think what's really important is that we can't change this as a community. What we need to do is broaden the use of safe technology. And over this time, we will first learn about the technology. We will build statistics. We'll make the existing workplaces safer. And along the way, we will learn what safety assumptions need to be built into guarantees and what don't. right? Like it's kind of hubris to say, oh, everyone will change. Like if only you put some statistics down, the entire world of manufacturing and transport or mining or whatever will change. It's an initial condition right now. Now it's a time varying initial condition, but it's an initial condition if you're designing a system to operate.
So for perceived safety, do you think sort of educating people about safety and making them more informed about safety will help with that problem? Like suppose surprisingly today, I educate everybody about the capabilities of a particular robot. Do you think that would fix the issue for perceived safety?
I mean, I think it's impractical, right? Like if you look at our robots are deployed in, among other things, automotive factories. Your average automotive factory has somewhere between 1 and 10,000 people who might work at that site for a large site. The most we can educate people on, like the bystanders around the robots, is the fact that the robots exist. That's the general level of understanding you can educate people on. So anything beyond that, and it's a little bit, it's asking for a bit much. It's this sort of thing you need to have, like society needs to iterate towards it. Like right now, if you go to a park, you might see drones flying around. And that's not necessarily a disturbing thing anymore. So we need to, continue to put robotics in areas where they can be guaranteed as safe, and not necessarily jump all the way right now to, let's fill our parks, our parks and our elementary schools with robots.
That makes sense. Naira, you have been working on real aircrafts for a long time now. So how do you define safety? Because I think with aircraft safety, I think aerospace as a field is much mature in terms of thinking about safety for a while now. So in your work, how do you define safety, and what do you think are the biggest challenge as we translate those notions of safety on something like, say, real aircraft?
So when we were working with NASA's aviation safety program, they had 4 words that we had to verify and satisfy: predictable, repeatable, testable, and safe. So safety was the 4 word in this combination. So we were going through very rigorous testing, and they had this 700-page mil-spec book that they were going through very rigorous testing through flight simulator, at first through obviously computer simulations that were done in our labs with students, then through flight simulators done by pilots where they were filtering the controllers and then taking to real world. And they had a bunch of scenarios that we had to verify and satisfy. And after that, it was going into real flight. And the standards required by FAA had to do with well-known notions of gain and phase margins, but there are scenarios that were defined by them. And then we go for Learjet, where we have already the real pilots on the flight. From the subscale commercial jet, we went to Learjet, and we had 3 weeks of ground run tests where my students spent the time in Air Force Base working with the pilots for ground run tests before the airplane can take off. Again, the scenarios are worked out with the Air Force people, marshals and generals. They have to sign off on paperwork. We work 6 months very rigorously. What are the failure scenarios that they can introduce on this variable stability jets? It's called VSS system, where they can introduce failures and the aircraft will have its own shutdown system when it's dangerous. When there are people on board, it has to be safe. And as we go through all of that, then we deploy the aircraft. So the safety criticality is a lot tighter defined when there are people and the aircraft is in the air than when there are people in a car and the car is on the ground. Because then when you're on the ground, the safety constraints have to do with constraints that have to do with path following, or the trolley problem, like ethics issue that has still to be addressed. What's better to kill, right? A woman with a child or 5 young guys? So the trolley problem remains unsolved. But in the air, any small thing, it's 350 passengers. So I guess some fundamental problems may long remain unsolved until some policies are derived. However, working with these team members from Air Force, pilots, flight test engineers, was a very good experience for students to learn how to work with different engineering standards that required to shape type of mentality and culture and bring it back into the development of theoretical methods. That's all I can say. And then, I mean, like Marco said, we can talk about these issues beyond one workshop for another 7 days and not be done. But briefly, I can say that it's a different cult when you deal with aerospace, real-world aerospace systems, aerospace industry. It's some type of different cult that you have to deal with. You have to respect it, first of all, and respect it deeply. And there are no shortcuts there. You have to walk every millimeter, every epsilon very rigorously.
That's very interesting, Naira. One quick follow-up question on that. So you sort of pointed out the role of simulation, I think also probably hardware in the loop simulation, if I understand correctly, for some of the work that you've been doing. Where do you see the role of simulation for, like other autonomous systems, such as autonomous cars, in thinking about the safety or in trying to verifying the safety of the system?
I mean, so there are a few ways to think about simulators and simulations. On one hand, when we're developing kind of robust adaptive methods and everything, obviously we want to have the versatility and agility of methods so we can develop them around reduced order models and still have robustness to all kinds of uncertainties, all kinds of uncertainty models, be it deterministic, stochastic, epistemic, aleatoric, and anything you can think of. On the other hand, you want to have the highest possible fidelity in different simulators where you can test these methods that have been developed around reduced order models. So developing high fidelity simulators can be helpful in terms of transitioning to real world systems. I have heard many pilots making statements that they have been trained in some high quality simulators, flight simulators, that have helped them to move from high quality flight simulator into the real airplane and fly on day one without any problem.
Interesting.
I don't think any of us have driven a car with that ease, right? So we were going through driving school maybe and learning to drive through back roads till we were getting on a highway. But I've heard pilots saying that they were trained in flight simulators and going into real air without any problem.
That sounds good. Thank you, Naira. I know we are coming close to the end of the session, and we discussed a lot of challenges for the safety of real-world systems. But next, maybe I would like to hear panelists' opinion on one challenge they would like the safety community to focus on for the next 5 years. So one of the things that you want to see solved in next 5 years, and maybe we'll start with Marco this time.
Difficult to make a ranked list. Let me mention just one topic that connects well with Naira, what Naira just said. Simulation is extremely important. Primarily, well, one of the main reasons is that at the end of the day, you want to make money with these systems, which means that basically you want to scale your system all over the world. And in order to do so, you need to have good simulators to have confidence that in the next place you're going to deploy your system, the system is going to work. And one of the biggest hurdles is, for example, in the context of self-driving cars, is to have good models for humans that you can really trust in order to trust your simulations. Autonomous cars obviously are going to have a very complicated interactions with other humans on the road, and the way that humans behave in different places on the world is completely different. So it would be wonderful if in the next 3, 4, 5 years, we really have good location-specific human models that are rooted in data and at the same time are controllable so that we can elicit different corner cases from the autonomy stack.
Like, may I add something to Marco? Like Marco said, humans are not scalable. That's very important to understand. And that's why even educating the students about this concept is a great challenge. Educating people to understand safety and everything comprehensively, how every aspect in it is important. While working with NASA, my biggest growth was there when I started respecting the engineering rigor, because my PhD was in math, and I always thought rigor belongs to math. No, when I work with NASA engineers, I gained great respect for engineering rigor. There are no shortcuts. I have to walk with pilots and engineers every step in their rigorous testing protocols. And without it, I won't get access to those real flights on real airplanes. And that's very important. And this comprehensive understanding that every step in a big process has to be extremely rigorous. That's very important, and the students must have this comprehensive understanding of everything. That's the biggest challenge, because some people like to say, oh, I just do linear control. Oh, I'm just a robust control person. Oh, no, that era is over. That was the 80s of the 20th century. Today, it's a different reality, and that's very important to understand, perceive, and accept. And reality is always right.
That's a very good point, Naira. So yeah, I mean, as a moderator, should not share my own opinion too much, but I think, yeah, I totally.
There are two things I learned from Boeing. One is the reality is always right. The second is the customer is always right. So you have to accept the two.
That's a very good point. So I'm going to move to Ryan next, because I'm sure Ryan has opinions on that. Ryan, what do you want to see solved in the next 5 years?
I mean, people are going to work on simulating and improving simulations, whether I say it or not. So I think the technical aspects and the research aspects of that aside, we really need to better discuss where simulation does and does not count, so to speak. In its current state, in the future state, whatever, we're not really talking about that, right? There's all sorts of discussions about, oh, we've simulated this many, in this many analog environments, we've run this many, call it shadow mode tests, or we've done this many, digital twins, but we don't really have any standard best practices on how that does count as a well-tried system. Like, what is the fidelity of simulation that you actually need? We're talking about improving it, but we don't actually have any goals, right? At what point does it count as, like, at what point does 1 kilometer of simulated driving count as 1 kilometer of real driving, for example? We don't know, right? The other thing, and I will, sneak in a second one as well, is we again, obviously I'm biased here, but we continue to focus on jumping all the way to the end, which is self-driving vehicles. Like, our company has neural networks running unsupervised in production. And we do this by a reasonably sane layer of safety, right? We don't consider them safe, but they're still running unsupervised in production. There's probably things that can be learned by the safety and research and machine learning communities on how that works, because we are able to build up that kind of experience. And I know there's a lot of other environments, like operational design domains and markets, where this is feasible, right? Not just us, but mining or agriculture or what have you, where you can do this. So I think there's some research to be done where you can rely on the real world to get some of this data without expecting the entirety of the self-driving vehicle problem to be solved.
Thank you, Ryan. And Felix, what would you like to see people solving in the next 5 years?
So I think the most exciting topic that I'd like to see solved is kind of this interaction of simulators or kind of partial models of the world and kind of the disconnect to the real world. Right, so be that in terms of, as Marco mentioned, like some kind of verification, right? Like, do I kind of do just testing and use the model to figure out where kind of I could easily find corner cases, but also just combining the two in general, right? Like, thinking not so much as kind of I'm a kind of a data person, right? I just do whatever policy gradients and whatnot, or like I'm a model person, I'm learning a model, and then I can kind of get my control toolbox. But I think kind of the really interesting research over the next couple of years will come at the intersection of the two.
That makes a lot of sense. I can have this discussion going on for hours and hours, but I want to stop here, and I want to hand over to SiQi so that we can also take some questions from the audience. SiQi.
So we have one question from the audience. So is it enough for our system to not actively cause accidents, or does it need to be actively participate in preventing accidents? And if so, what degree does the system need to have that capability? Maybe we can start with Ryan.
Sorry, I'm just trying to understand. Okay, I'm reading it on the website, or I'm just rereading this on the website here. I mean, I think it is enough for a system to not actively cause accidents, but causing an accident does need to take into account those second and third order items, right? Like following too closely, for example, and then slamming on the brakes, that can cause an accident, right? Fortunately, in many cases, there's a lot of understanding, whether it's in case law, for example, on what does and does not count there from a human perspective, so we can look at that for guidance. Yeah.
Okay, thank you. With Felix.
So I'm not 100%. I'm trying to get to the website to read the question as well as Ryan, but so I think it's not so entirely clear to me from what I understood. How I understood the question is the difference between actively avoiding and not causing. That seems right. Like says ultimately, right? Like the outcome is, I think, the most important thing, right? Like also if we want these things to be accepted and to actually be kind of regulatorily kind of approved, essentially the outcome is in the end what matters, right? That we don't really cause any accidents, that people get build kind of trust in these systems over time.
Okay, thanks. Yeah, I guess my take to the question is more like more human-centered environment. What kind of measures we should have in mind to avoid, I guess, maximizing the possibility of having accidents. Maybe Marco?
Is it a question about how we reason about interaction with other humans when define safety metrics?
I think it was like, what considerations should we have in mind to prevent accidents as much as possible? More real-world environments, such as, for example, autonomous cars, where we have more unpredictabilities around human interactions.
Right. Well, first of all, it depends a little bit on the level of automation that you want to have on your vehicles. So if you're talking about advanced driver assistance systems, then probably it is enough to make sure that the active safety mechanisms that you have in place are trustworthy. But if you go to very high level of autonomy, as Ryan mentioned, then it is a duty of the robotic vehicle to also think about those second, third order effects in terms of what I should not do that might trigger an accident downstream. That's where the notion, for example, of responsibility that I mentioned before comes into play. So the short answer is that it really depends on what is the level of autonomy that you try to enable. Depend on that, you may need to include, I really like this definition that Ryan had of second, third order effects into the design of your decision-making logic.
Thank you, Marco. Unfortunately, in the interest of time, we have to conclude our first panel discussion today. Let's give a huge round of applause to all our panelists for joining us and sharing their thoughts. And thank you to all the panelists for joining us.
Thank you for having me.
Thank you, Naira. With that, I hand over to Animesh for the next panel discussion.
Thank you so much. This was very exciting, and I think, as we had hoped, it shed a lot of light on many of the interesting questions. And as was pointed out multiple times, defining safety itself is an open problem, let alone the algorithms to get there. So now, next part of this workshop is about challenges and opportunities. And this panel discussion will focus on ideas of challenges and opportunities in safety guarantees for decision-making in real-world systems. What are examples of technical problems in safety for real world, and what sort of opportunities can be leveraged using theory and data to ensure deployment in real-world systems? And co-moderating with me is Melissa Greeff. For those who just joined us, I am a faculty at University of Toronto and I work on robot learning. And Melissa Greeff is a senior PhD student at University of Toronto, a woman grandmaster in chess. And because she has solved models where models of the world are known, so her research focuses on decision-making under uncertainty instead. With us, we have esteemed set of panelists in different areas of applied robotics and industrial R&D. First, we have Wei. Wei is a principal engineer and tech lead manager for the Planner machine learning team at Waymo. In her role, Wei is leading the efforts on safely integrating machine learning into prediction and planning for autonomous cars. Wei received her PhD from MIT and now is at Waymo. Welcome, Wei. We also have Karol Hausman. Karol is a longtime friend and a fellow from Stanford. Karol is currently a senior research scientist at Google and Google Brain and an adjunct professor at Stanford. He has received his PhD in robot learning from University of Southern California, and he's interested in enabling robots to autonomously acquire general purpose skills with minimal supervision. And finally, we also have Alexander Herzog. Alex is a senior roboticist at Google X and received his PhD at ETH Zurich while collaborating very closely with the Max Planck Institute. His research includes robot manipulation and grasping for humanoid robots. Welcome, Alex, and welcome, Karol, as well. I'm very excited to have you all. And now I would like to give you the opportunity to present a maybe 2-minute opening statement on the topic of challenges and opportunities on decision-making systems. Let's start with Karol, and then we'll go to Wei, and then Alex. Karol.
All right. Hi, everyone. Thank you very much for having me. This is a great honor, and this is a really great workshop, so thank you for organizing it. I wanted to start off by saying that I don't consider myself a safety expert per se, but I'm really interested in robot learning, and I think that's where a lot of opportunities and challenges lie for safety as well. So safety is a very interesting and important topic, and I think a lot of the panelists so far have been talking about safety when it comes to other systems where you don't really want to get in contact with anything, and that's where you are safe. For example, in self-driving car or things like that. So in my work, I work mostly on manipulation, robotic manipulation, where contact is basically exactly where manipulation starts. So all of manipulation is contact. So I believe that in manipulation, reasoning about safety becomes even more tricky because it's really tricky to say, it's really tricky to define where a system is safe or where it's not. And we don't really have a clear boundary, and it can be really tricky to even say whether the system is safe or not. I also agree with some of the previous statements in the previous panel that we should consider safety as a holistic system where safety of individual components is necessary, but it's not enough to say that the system will be safe. And also with what Felix said about models and assumptions that very often we can make, but very often we can throw them out of the window once we have robots in the real world and doing things, working with people, and being deployed in people's homes, for instance. And especially as systems become more and more autonomous, I feel like we might need to move away from very strict definitions of what safety is and very clear boundaries to something where we get to define safety as the robot is working. So I think we can show examples of what safe or unsafe behaviors are, and we should use learning to learn from these examples and to learn from them as efficiently as we can, because I don't think we'll be able to sit down and write down all the different unsafe conditions that the robot can find itself in so that we can optimize them away.
Let's carry on. Thank you, Karol. So let's carry on with Wei.
Hi, thanks everyone. It's really a great pleasure to be here. Start sharing my thoughts and learning from the research community on how to combine the traditional robotic algorithms and the learning-based algorithms. I think this is a very important area for autonomous driving because for autonomous driving, we need to deal with very diverse, complex situations where we may need to interact with tens or hundreds of agents who could be humans or such as pedestrians or cyclists or cars controlled by human drivers. So as we know, humans are stochastic by nature, and also the social interactions between the agents can be also subtle and hard to model. So in general, I believe we need to combine both approaches to leverage the advantages of each method to maximize safety. And I agree with a lot of points raised by the previous panel. For example, like how to define and measure safety, and also like overthinking the theoretical approach as a driving force to design algorithms. I felt these are really great points. And I'm very glad to see the two communities are already pushing research from both sides to meet in the middle. For example, I've seen research on learning-based control algorithms, or like research from ML side incorporating constraints in learning-based approaches for better safety guarantee, which I think we should keep pushing on both sides. So yeah, that's my high level.
Thank you, Wei. Alex?
Yeah, hi everyone. Thanks for inviting me to this workshop. It's great to see all the interesting points of view. So I'm working at the Everyday Robot project at X. We have robots that that drive around and have a manipulator, and our goal is to solve tasks in human-inhabited environments that are useful for people. And as such, we naturally interact in in a lot of clutter, in some semi-structured environments and semi-structured tasks. And I'd also not consider myself a safety expert as Karol, but we do need to face it, obviously, because you have robots that drive around next to humans, that interact with objects that belong to humans, and there you have a we see a broad spectrum of safety concerns, starting from trying to not break the robot, over driving around robots in a safe way, but also without intimidating people, not driving up to them very closely. So there is kind of a gray zone from safe to non-safe. But also, yeah, most importantly, as we start interacting with objects, we need our robots to learn to go into contact and do something useful, but at the same time not break robot and environment. And that's where it starts getting hairy. And here again, yeah, if we were to make full guarantees of safety, we would never put a robot into a human environment. On the other hand, if you don't have any safety guarantees, it would break the first day. It would be useless. So it's kind of a juggle between usefulness and safety.
Thank you. Thanks a lot, Alex. Over to you, Melissa.
Okay, so you've all briefly touched on this already, but perhaps you can give some more specific examples. So what are the key features of your problem space in your application? We have with Waymo and self-driving. We have mobile manipulation in the home that make guaranteeing safety challenging. So for example, is it the number of agents? Is it the stochasticity? Is it the level of precision? Is it the perception feedback loop? What specifically are the key features in your problem space that make safety challenging? And let's start with Wei.
Yeah, I think I've already touched upon in my like a beginning statement. I think in general, the complexity comes from like we need to deal with the complex situation involve like human agents, and in general, it's very stochastic, and like sometimes the human, the goal and intent are not completely observable, and also the social interactions are in general very subtle to model. And we also sometimes have to think about the defined, predefined limit of computational resource. That's another thing for autonomous driving. So we need to really get all the computation finished within certain amount of time. And also the noise you mentioned, like we have noise we have to consider in every layer of the stack. Like some are like perception noise, some are just like different computational noise or prediction noise. I think we have to take into consideration all these different noise. So in general, we're really dealing with a high-dimensional stochastic environment, and we have to consider all these factors. Some of the factors are not independent as well. So I think these are all the challenges we are dealing with for autonomous driving.
That's great. What about Karol in your application?
Right. So we're looking at robots that are able to do many different things, potentially anything in a human-driven environment. So let's take an environment like an office, where we want to have a mobile robot that roams around and does useful things for you that you can talk to, and it should help you accomplish some of the tasks. So one aspect that we started looking into is generalization across tasks. So can you ask a robot to do something even though you've never asked it to do it before? But maybe it might have been in similar scenarios before, but maybe didn't exactly do the task in this scenario that you're asking for right now. And what we often find in these cases is that we don't really know how the robot might fail and in what way it will be unsafe. So some of these things you can define up front, but for instance, if you ask a robot to bring you a mug, maybe you haven't thought about the fact that the mug shouldn't be upside down. That was kind of very obvious to you, but it's not obvious to the robot. So very often we find ourselves in a situation where the robot does something, and only once we see it, we can tell, well, this was unsafe. We shouldn't be doing this. Then the other aspect, which I think is maybe a little bit more unique to our setting at Google Brain, is that we are running a lot of robots, and at the same time, and we're collecting a lot of data 24/7. So these robots are interacting with the environment all the time, and we want to do this with minimal human supervision, and we want to be collecting data, as much data as possible. So what that translates into is that we have all these robots that are doing all kinds of crazy things. And when you have this many robots, then very often, if there is something that can go wrong, it will go wrong. So we see all kinds of weird cases how the robots might fail. So another aspect that we're looking into is how can we make them safer, not necessarily because this is what the application right now demands, but mostly because we want to collect much more data, and we want to collect data autonomously.
Alex, is there anything different about your application compared to Wei's and Karol's?
Well, my application is very close to Karol's because we collaborate. But maybe what I'd like to add is so we work on real-world problems. Our problems are not defined by the algorithms we want to show, but rather by the by customer needs or by what provides value. And that forces us into a regime where we have to address kind of the broad spectrum of the things that you mentioned. There is some aspects of the tasks are modeled, and we need estimators for that, and there is estimation noise, in particular for navigation, for example, or estimating some objects like tables or so in the environment. And there we use more optimization-based, constraint optimization-based techniques to overcome safety. But then also we work in a human environment which is full of clutter with a lot of things that cannot be modeled. For example, the constraint Karol mentioned with the cup, but there's also a lot of other objects that are not registered in some database, but we need to learn to interact with them. And then in our setting, what's also interesting is we explored a lot of sim to real. That means we do a lot of training in a simulated environment that is similar to the real world, but not exact. And in the simulated world, you can go and break things, and you can have the robot explode, and you can learn from that, and hopefully generalize to the real world. And that's also something that we work with.
Wonderful. I think this is very insightful. Both Karol and Alex did mention that they don't consider themselves safety experts, but I do believe all three of you actually are system builders, in the sense that you are pushing the edge of what is possible in research and putting this out on increasingly larger and more complex systems that was possible earlier. And a good follow-up here for everyone, both in academia and potentially even others in industry, is first question is, what sort of traditional control methods can you use in your applications? And if you're not using them, what is limiting or preventing you from using them? You still have to build systems, whether you are a safety expert or not. You still have to build what you would say fail-safes. You don't want the robot to keep dying every 15 minutes anyways. So what do you do right now? Maybe let's start with Alex.
Yeah, that's a good question. So I think one factor that's limiting us from using traditional approaches is just because it's limited in expressiveness for the type of problems, the type of manipulation problems that we have. So you quickly a problem becomes either too hard to model. So imagine you have like a bin full of objects and you need to interact with that. Or on the other hand, what happens is maybe you can have some conservative model, but that conservative model starts limiting you from achieving the task in an optimal way, or having the robot learn to achieve it in an optimal way. So for example, a common application for us is to optimize object picks per minute. So basically pick objects as quick as possible and do something with them. And you can imagine, as you impose constraints on the context that you can make, or the type of objects that you can detect, you will impose a performance upper bound. So I would say this is one of the issues. The other one, I think, was already mentioned, is we have just limited compute, and if you need to simulate forward your constraints on on a lot of objects in the outer world, in the external world, self-collision, and so on and so forth, then your robot gets really slow really quickly.
Karol, would you want to add something to it? Because I think you are closest to what Alex works on.
Yeah. So I agree with what Alex said. We work on very similar things. I would add maybe to it one more aspect, which is generalization. So as we want to have robots to do many different things in the real world and operate with many different objects, even objects that we haven't thought of before, or do tasks that we haven't thought of before. When we think about applying more traditional approaches, I think that's where the main bottleneck lies. So if we want these approaches to generalize to things that we haven't thought of before, they usually fail, and we need to look back into this particular scenario and incorporate certain things into the model or into the approach itself, into the plan, so that the robot can accommodate this. And we just didn't think that this was scalable to do this way. So rather we picked the data route, where we can collect a lot of data without necessarily coming into every scenario and putting more information and more constraints on how to solve it, and just let the data kind of drive the generalization process.
So I think both Alex and Karol pointed these problems and issues in manipulation settings where safety is important, but safety is not fatal either. So if the robot drops an object, well, there's only lost sort of productivity, no bad PR for Google. What about Waymo? How do you sort of think about conventional methods in safety as you build your systems?
Yeah, I really want to echo the previous two panelists' points. I feel in general the traditional approach normally assume we have some prior knowledge and some assumptions on maybe some known models, so that we can provide some safety guarantee, which I already mentioned. It's pretty hard to do for autonomous driving because we're working with all these human like agents and sometimes unpredictable nature of human. I feel so then we have to consider data-driven approaches. I also want to echo the point on the generalizability, like how to think about generalize better to new situations, and because we need to think about high severity cases might be rare, and some like unseen scenarios. How can we still be able to handle all those scenarios? So I feel in general, learning-based approaches might work slightly better on those. But on the other hand, we are also thinking about different ways to say how to get all these constraints, the method from the traditional approaches to like combine with learning, like how to, for example, adding the inductive bias into the model architecture, how to incorporate constraints into the model. And in general, I think autonomous driving system is a very large, complex system. There are many sub-problems as well. And we're trying to figure out what sub-problems might be better for learning and what problems might be better whenever we can have safe assumptions or prior models, we can potentially also leverage traditional approach.
Wonderful. Over to you, Melissa.
So we have a follow-up question for Wei from the audience. So you brought up many interesting factors that make the stochasticity of the system high dimensional. Is there any particular factor among them that is less tackled and unsolved in academic research that you find important and challenging for academic researchers to focus on?
Yeah, that's a very great question. So I feel the previous panel actually touched upon like models for humans. I think that's definitely an interesting aspect. I think a lot of the previous approaches are still based on like, this is how we think about the normal human behavior would be, but not quite like based on data or like capture enough the nuances of human behaviors. And I also talked about the interactions. It's not just about the agents in the isolation, but also agents in the interactive environment. I think that's definitely one of the big challenges for us.
So that's pretty cool. I think this is something that was also mentioned previously. Marco mentioned explicitly that a lot of the systems that we are building, AV is a very good example, but I think manipulation and mobile manipulators are not very different in that sense, that these systems are often layers of systems essentially, right? There's some sort of planning algorithm, there's perception algorithm, maybe a localization, a mapping system, some sort of like cognitive decision making. And when we think about each of these systems independently, perhaps we can have their own assumptions and maybe even their own guarantees / assurances. Maybe they hold, maybe sometimes they're not. But how does one guarantee safety of after integration? Because essentially, if I were to buy the future everyday robot at any point of time, I don't really care what happens to the wheels and to the camera separately. What I need to know is, will it cut my apple or not, kind of thing, right? And of course, this is a tongue-in-cheek example, but really, that's a practical problem. How do you guarantee safety of these sort of intermingling components? Maybe we can start with Karol this time.
Yeah, I think that's a really good question. And I'm wondering myself, actually, how we can do this and whether it is possible to have a guarantee on a robot that is this general. So one thought that comes to mind is maybe, the way that we've been thinking about safety, I think, for a long time and very successfully has been in terms of safety guarantees and very strict assumptions that we cannot break and safety guarantees that we are very certain of. maybe as we move to these very human-centered environments and we want robots to do many, many things, maybe we should treat safety a little bit differently, a little bit more like how we treat safety with humans, for instance, right? Like you can trust someone that they'll probably do the right thing, but sometimes they won't, and maybe, maybe it's okay. Maybe he'll just tell them and they will adjust next time. So I think as robots become more and more capable, I think it will be the case that they won't be 100% safe. But maybe the times when they're not safe, we'll be able to incorporate our feedback and make sure that something unsafe happens, at least in manipulation world where there's no big consequences really. Where something unsafe happens, it only happens once, and you have to just tell them that this is not the thing you should be doing, and then it can incorporate the data. It will never happen again.
What about you, Alex, here?
Yeah, I think I agree with Karol. If you want to have a robot that is not in an industrial setting, guarded by a cage, I think you have to accept that these robots, they will, they will exceed some certain safety boundaries. Now, for what we do is there are certain things that you never want the robot to do, and where you have some classical estimators of that part of the state of the world. And you can use techniques like constraint optimization to guard the robot from violating safety constraints there. But then again, it very quickly gets into a mode where you need the robot, have it explore, to touch things and do things that potentially break something. And I believe the only way around there is to find the balance where it's acceptable to have the robot learn to become safe, and where it's not.
And would you sort of want to add anything, Wei?
I don't know whether this is relevant. I think the panel also touched upon this, is how to combine the component level evaluation to the system level evaluation. I think at Waymo, we always need a rigorous evaluation and verification at all different levels. Typically, we have like model level or module level metrics and tests. And we also have system level metrics and tests. And the system level, we also combine simulation, structured testing, and the public road testing to estimate our system safety. I wonder if that's more like an industrial standard way of doing things to better understand, assess safety.
I think that's
I would also maybe add
reasonable.
one more thing regarding one of the previous questions about the role of academia and all this. So when you look at safety as a learning problem at this higher level where you can't really evaluate things very easily, I think there's one nice opportunity, which is we start to try to combine different data sets collected in different labs with different robots and so on. And usually these different robots do very different tasks, which makes it really tricky to have one big setting that you can jointly optimize. However, safety is a little different. For whatever task you're doing, we all define safety and understand safety in a similar way. So whether you have a data set collected in Toronto or at USC or Berkeley or anywhere else, if the robot did something unsafe, we probably all consider it something unsafe, so we can all optimize for the same kind of task. So I think as that presents an opportunity that we can start joining these data sets and potentially thinking about safety across robots and labs.
That's actually a very neat idea. I think that would be a very cool effort to definitely try out. One thing that is piquing my interest here, all three of you in some way pointed out that practically what we really have to do is to basically identify corner cases as we go and then fix them as we go. A curious question here is, first of all, what mechanisms do you have in place? Maybe you can give examples or a high level to identify these corner cases in the first place automatically, because these systems are at scale. You're not going to be standing there looking at it. When they do happen, what sort of algorithm do you actually employ to ensure that the same error does not happen again? Because ML algorithms are notoriously bad for learning from like one or few examples of particular kind. So maybe we can start with Wei this time.
Yeah, this is a really good question. I think in general, finding the long tail corner cases is not easy, but it's also very, very critical for us. First of all, we drive a lot. So we drive tens of millions of miles. We also have like billions of simulation miles. So we kind of trying to really maximize the data we can collect to understand, to collect the corner cases. And second, we developed tools to discover new issues and mine hard and long tail examples from our log. Once we find such like corner cases, we also develop very targeted evaluation metrics and data sets to measure and track our performance on those long tail scenarios. And for those cases, we try to also double check if our algorithms are general enough to cover these long tail cases well. And we sometimes have to even tweak our algorithms for machine learning. It could be just data augmentation strategies, or even some special data model design techniques to cover both average cases and tail cases. But I have to say, in general, that's really a challenge for machine learning community, like how to deal with long tail, and especially that could imply data scarcity, right? So I think that's really challenging a lot of like the fundamental assumptions for machine learning. I felt that's very exciting topic because I came more from machine learning community. So that's very, very, very useful and important problem to solve.
How do you guys handle this problem in manipulation or mobile manipulation? Maybe Karol goes first and then Alex.
Yeah, so this is a big problem. We run into these corner cases quite often. We usually see them because we run robots overnight, and then we come in the morning and then we see that something crazy happened. I remember Sergey Levin told me a story where he was running the first ARM farm together with collaborators, and came in the morning and it looked like a crime scene. There was just like red everywhere on all over the bins and so on. And it turned out that there was an open marker that the robot picked up at some point and started, drawing on all the bins. And I'm not sure how to deal with corner cases like this, but we see cases like this a lot. So we also use simulation. We do data augmentation, similarly to what Wei described. We also make sure to record these cases so that we can learn from them later. And so we are still figuring out the best way to do this, to make sure that we have enough of these so that we can learn from them. But I would also maybe challenge a little bit the assumption that we need a lot of data per case. I think we need a lot of data in general, but we do see that that neural networks pre-trained on large data sets can actually fine-tune to individual cases relatively quickly with very small number of data points. So I believe that if we have a large enough data set with large enough support, then we wouldn't need that much data to make sure that we can fine-tune it to our particular safety case.
Alex, would you like to add anything?
No, I think that's the spectrum is pretty well covered. So it's fine tuning is one of the things, as well as replicating the case in simulation, where you can generate a lot of data. As of examples of things that went wrong, there's tons of them. As Karol says, you come in to the office and you have robots tipping over the tables lying next to the robots, or something is ripped off. And no one stopped the robot, so it kept actually, doing the task while the environment was not in place anymore. Things like that. And yeah, you rely on tools where raters go through the data and annotate things that went wrong.
So that's pretty cool. This has been a wonderful discussion, and we are nearing towards the end of the time, but I do want to ask a more controversial question, and I request the panelists to give sort of binary answers rather than gray answers. Gray answers are easy. Do you think the best solution to safety and learning is better real-world simulators, or can we go without them? It's not yes, no, but near yes, no answers would be appreciated. Let's start with Wei.
Okay, can you repeat the question again?
So do you think the best solution to this problem is better real-world simulators, or can we do without it?
My answer is probably yes. So I do feel I'm a like strong believer on rely on simulation on this type of problems. I feel that can help a lot with evaluation and also data collection. But in general, it's definitely not trivial, like how to even improve simulation for better scalability and realism. It's still a very challenging problem for us. But I do feel, at least my personal opinion, that's kind of the direction to bet on.
Wonderful. What do you think, Alex?
Yeah, I think for manipulation, the question is not as hard as for autonomous driving because, again, our safety constraints are not as strict, I would say. And with reinforcement learning in particular, we do have experience with fine-tuning, where even on a smaller data set, you can fine-tune and learn particular behaviors. So I would go with we can do it without simulation, but it just makes life really easy if you have simulation.
Karol?
Yeah, so for a long time, I've had the same views as Alex on this. I kind of view simulation as a crutch that would help us. It is super helpful and can give us a lot of data. We can augment the data. We can generate it in all kinds of different scenarios. So that was really cool. But I don't necessarily think that it's necessary. Like we can, if we had enough data in the real world, and I think we might have enough data at some point, especially once we start combining data sets from different experiments, different labs, and so on. I think the problem is solvable. However, recently I started thinking about evaluating these very general autonomous systems. And I think that's when simulation is actually extremely important. And it's really, really tricky as as the systems become more autonomous, it can do more things, it can get in unsafe situations in more cases and kind of can fail in so many different ways. I think simulation would be extremely important just to make sure that we can evaluate these systems better. So I would say I changed my answer and I'd say simulation is necessary, but for evaluation, not necessarily for development.
Wonderful. I think this has been a wonderful time chatting with all three of you. Thank you for making time. For everyone who is joining us late, we had a wonderful discussion on what makes real-world challenges and applications of safety hard. And it appears that generalization to multiple skills, a long tail of corner cases, is still a hard problem to solve, both from a perspective of algorithms and just like machine learning is not there yet either. And our panel slightly sides with building simulators than not. So that would be over to you going forward with benchmarks and evaluation mechanisms. Angela.
Great. Hi, everyone. So we are immediately transitioning to our very last panel with exciting panelists. I'll share the slides. So this last panel focuses on benchmarks and evaluation metrics for safe robot autonomy. And we just heard that simulation could be one way to benchmark or evaluate safety for these new robotics applications. So the question really we want to focus in this panel is how can we test and evaluate safe robot algorithms? And it's my immense pleasure to introduce our panelists today. Our first panelist is Professor Ani Mesunda. Ani is an assistant professor in the Mechanical and Aerospace Engineering Department at Princeton University. He also holds a part-time position as a visiting researcher at the Google AI Lab in Princeton. Ani is interested in approaches that really push the limits of what robots can do while providing formal guarantees on their safety and performance. So a very warm welcome, Ani. Then we have a second panelist. Byron Boots is an associate professor in computer science and engineering at the University of Washington. He's also a principal research scientist at NVIDIA. Byron leads the Robot Learning Laboratory, and in his research, he has used learning for planning, control, and estimation, and has done both end-to-end approaches as well as more model-based approaches. Welcome, Byron. And our last panelist for today is Vincent van Hoek. Vincent is a principal scientist and director of robotics at Google. His work spans robotics, machine learning, and audio and visual perception. And at Google, he has participated in various efforts of robot algorithm benchmarking and evaluation. We are very excited to have you here, Vincent. Welcome. And the panel is moderated by myself. My name is Angela Schöllig. I'm an associate professor at the University of Toronto, and SiQi Zhou, who is a senior PhD student in my cohort. Just as a reminder for everyone who joined late and for the panelists, well, the structure is as follows. We start with a brief opening statement of all panelists, and then we go into moderated questions, and we also include the questions from the audience we receive on various platforms. So before we start with the opening statements, I just want to briefly set the stage. So from my perspective, robotics challenges and competitions, such as, for example, the DARPA challenge, RoboCup, or the Amazon Picking Challenge, have really led to significant advances in robotics. And similarly, open data sets and associated leaderboards, such as the Kitty Vision benchmark suite, have defined clear research problems and allowed researchers to compare their algorithms and make progress towards a particular problem. In addition to competitions with real hardware and benchmarks based on data sets, there have also been some recent simulation environments, for example, those from OpenAI, that have been widely used in the reinforcement learning community to test and compare algorithms. Now, all of those have not had a very specific focus on safety. So really what I'd like the panelists in the opening statement to comment on is, where do you see the role of benchmarks in evaluation metrics going forward in robotics? And which limitations do you see? We'll start with Ani.
Thank you very much, Angela, and thank you to all the organizers for inviting me to participate in this panel. So I'm going to start by highlighting 2 points that I think are important when we're thinking about benchmarking for robotics, and specifically benchmarking for learning-based approaches to robotic systems. So the first point is the need for benchmarking and also benchmarking procedures that allow us to quantify the ability of learning-based robotic systems to generalize to novel environments. So how can we measure the ability of a robot to operate safely in environments that it was not presented with during its training time? I think in some sense, generalization is a core technical aspect when we're thinking about learning-based approaches to robotics, but we currently don't have really good ways of measuring or even necessarily quantifying generalization. So as a simple example, if we think about a robotic manipulator that's been trained to grasp a certain set of objects, so let's say mugs, but then at test time you present it with a different set of objects, like let's say balls, for example. How do we even quantify how different the test objects are from the training objects? So in this case, how different are balls from mugs? I don't think we have really compelling ways to measure this kind of generalization, but I think doing so is going to be a critical component in kind of measuring progress on learning-based approaches to robotics. The second point I want to make is a slightly broader one. So I think different research groups within robotics often make pretty wildly different assumptions on the robot, its sensing capabilities, its environment, and so on. So for example, some groups might focus on low-level control problems like stabilization or trajectory tracking, while assuming that the robot has good state estimation and kind of ignoring perception-related challenges, while other groups might focus more on perception while making assumptions maybe on the fully actuatedness of your robotic system. I think potentially benchmarks in robotics could help drive the community as a whole away from making very restrictive or unrealistic assumptions and promoting approaches that improve the end-to-end safety and performance of our systems. So I think recent benchmarks and simulation environments have started to move towards this, but there's still a long way to go.
Great, thank you so much. We will go next to Vincent because I know he has been at least internally at Google, but also externally promoted certain benchmarks, and I would love to hear your vision.
Yeah, thank you so much for the invitation. One thing that's been challenging, I think, for benchmarking in the context of safety is that there's no such thing as a safe robot, or at least the robots that are safe are only the extremely boring ones. There is safe applications of a robot. And so you always have to really think about safety in the context of a use case and in context of a specific application scenario. And attaching safety metrics and safety validation to existing tasks makes the problem very difficult to study in isolation. There are benchmarks out there that exist that try to isolate the issues of, robots needs to not collide with things, or robot needs to not apply too much force on things. But reasoning about them in isolation kind of ignores the bigger picture. So one question is, how do we go from there? I was last week attending the International Robot Safety Conference, and it's amazing to me how different the problems that are being addressed there, that are being brought up, how different they tend to be from the kind of cases that we make for safety in the academic community. And so I'm hoping that one path could be to really get the industry to help us define more of those benchmarks and what really matters and what are the gaps between what our technology is today and where it should be in the future for at least the use cases that we currently know of. Of course, we should also study the use cases of tomorrow that we don't have, a good, that industry doesn't care about yet. And that's where a lot of the robots in human-centered environment really come into play. And that's a super interesting challenge that, Marco talked about it in the previous panel. There is a huge challenge there. How do you evaluate safety in the context of human contact, human interaction? You cannot really evaluate unsafe events that involve people, and so you probably have to simulate them. And there is a huge gap, I think, in simulation between where we are today in terms of what we are able to simulate in terms of complexity of the simulation and realism of the simulation in the context of having actually humans in the simulation, and where we should be if we want to enable a lot more autonomy. So I think from a research standpoint, there's a very interesting gap there. How do we really bring humans into the pictures? I have some ideas around there, but maybe I'll stop there and let the panel comment more on all the different aspects of benchmarking.
Thank you so much. Yeah. I appreciate your point of working together with industry and also highlighting this gap in the human modeling, which is exactly those application cases where we need a lot of safety. So Byron, I know you have worked with real robots and done amazing things with real robots. What do you think about benchmarking?
All right, Angela, thanks a lot for inviting me. I want to start out by just saying that I'm an academic and I feel very underqualified compared with some of the folks in industry for discussing safety. I mean, they are driven by real world concerns, and I think it's important to listen to what they have to say. Let me start out by just talking briefly about safety and then just some views that I have on benchmarks. So I agree with some of the previous panelists in the last session that it's really hard to guarantee safety for learned systems. And I think it's extremely important to accept that in the real world, robots are going to make mistakes. And one of the questions that we have is, how do we get society to tolerate those? How do we minimize the impact of those mistakes? And how do we get robots to be able to recover from some of those mistakes? In my own work, one of the things that we think about a lot is how structure and interpretability can be used to help learning systems, both in terms of being able to generalize to previously unseen cases, and also to provide the designer some feedback as to kind of like what's going on with the system. And so in that vein, I think in particular models and real-time simulation are super important in the design of even a learning robotic system. And even simple models can be extremely helpful for thinking about these notions of generalization and interpretability. So we're thinking about this while we're designing systems which will actually work in the real world. With respect to benchmarks, benchmarking is like a huge area, right? It's a sort of an entire area that folks are thinking about, like within the robotics community. And there's a lot of different ideas about how to benchmark robotic systems well. Just from my own personal perspective, I'm a big fan of benchmarks which are independent of a robotic system. So what I mean by that is thinking about a benchmark which is basically a task. And this helps with generalization. So for example, I could use whatever robot I have in my own lab and see how well I can do at a task. And you can have different types of systems which can try to achieve a task in different ways. The concept of a race is sort of my ideal of what I think a good benchmark should look like. So humans have used this idea forever, right, for benchmarking themselves, but also animals, machines. It's something that is very easy to specify. It could be something which is like course or task specific. And it allows basically all comers to just sort of show up and see how well they can do and have a single number which possibly allows you to compare these different systems. So race is a very general concept, I think. So it could be something like get from point A to B as fast as possible, but it could also have to do with assembly or minimizing interventions or trying to keep things even as safe as possible while completing a task and also having some objective like go fast. In my view, benchmarks must be real world for robotics. I think real world benchmarks are the thing which brings out sort of latent problems, which are sometimes difficult to see when developing a robotic system. And sort of tying this back into safety, I really like the idea of using real world benchmarks as something which drives the development of safe systems. You make a benchmark which is hard enough, then it could be really hard to actually complete that benchmark without causing issues or allowing the robot to sort of enter into unsafe states. And so I'm thinking about hard real world benchmarks which maybe are in less engineered environments or scenarios are really interesting to me for then kind of backing out and thinking about the development of a safe system and then how to accomplish that. All right, so that's my sort of initial thoughts on this, but I'm happy to sort of discuss things more as we go forward.
Thank you so much, Byron. This is great. You already brought up, important features of what a benchmark should have. It should be real world in your opinion, and should be centered around a task. Maybe we'll go ahead with the question and around what do we think is missing in current benchmarks with the vision of, using these benchmarks to really drive research forward and lead to safe robots in the real world. So you already brought up some good points. Maybe we'll continue with Vincent. Do you see like specific features that are missing that you would love to see in a next benchmark that is adopted in academia and industry?
Yeah, I completely agree with Byron that for evaluation purposes, a benchmark should ultimately be a real-world benchmark. And you can use all the simulation infrastructure as a validation, as a development environment, but then ultimately your goal needs to be anchored in the real world. My team, we have 10 benchmarks that we are working on in parallel that we have codified as an evaluation metric and a setting that's somewhat agnostic to the actual method used to solve the benchmark. They're all defined in the real world, and those are the goals that we are pursuing. I think one of the challenges for a real-world benchmark is obviously accessibility. It's very difficult once you can basically define your benchmark in your own lab, making it portable and accessible to the rest of the world is a huge challenge because the subtle details of the benchmark definition can actually matter quite a bit, particularly for things like safety, where it's all about rare events and like the subtle, the very subtle configuration of your benchmark can really affect where you are. We're trying some experiments right now where we're trying to figure out to what extent we can sort of have a fixed physical setup and give remote access for people to be able to benchmark themselves remotely on those. Nothing concrete that we can share immediately, but I think that's a one direction that I'd be very curious in pursuing and see pursued more. How do we actually enable replication without having to replicate the physical setup, but by just the virtue of enabling remote access? A lot of the work that we do today has by necessity become remote, and we've kind of entirely operationalized our robot lab to be accessible remotely by our collaborators. How do we make that something that can be generalized is a really interesting question, particularly because it stresses the issue of safety and in all sorts of ways, like making sure that a naive user can actually safely or a user that doesn't have the right level of experience with the setup or has never physically seen the setup can actually do something meaningful in that environment in a completely safe manner for everyone involved. So very, very interesting direction. Probably not the only solution out there, but really accessibility of safety benchmarks is, I think, a really key topic that we should find ways to address in the community in general.
Yeah, this is great. So I do think the portability to the rest of the world is almost another step, right? Once it works in your lab and is safe, how would a similar setup be safe in another environment? This is great. So just one follow-up question before I move to Ani is, in your current benchmarks at Google, what role plays safety there?
It's often the bottleneck. It's often a very central bottleneck in everything we do. We work a lot on machine learning for robotics, right? And for us, because it's like Karol was mentioning in the previous panel, everything we do is conditioned on our ability to acquire data semi-autonomously or completely autonomously. And so safety comes into play not just at deployment time, but during the learning process, when your robot is frankly stupid and is not doing anything that is meaningful or that has you can put any guarantees on. It will explore, it will fail. And that's the kind of data that you want to be able to collect so that you can improve. So understanding how safety can be plugged into the actual learning process as opposed to just the deployment process is a fascinating challenge, because basically machine learning doesn't like constraints, right? Machine learning likes smooth losses, likes to have gradients everywhere. Every time you put a barrier somewhere that says nope, you can't do this, that kind of ruins all the learning signal and that makes it very difficult to reason about how to train a system. And so going over that barrier and understanding how we do safety in the context of learning is a fascinating topic. And I think there is a lot of research that can happen in that setting that the community hasn't completely focused on quite yet.
Yeah, great. Annie, from your perspective, what would be the perfect next benchmark? What is missing in current benchmarks, and what would you like to see?
Yeah, I would say there are a couple of things that are missing in current benchmarks. So I think one of the points is the one I highlighted in the opening statement. A lot of the existing benchmarks kind of make very specific assumptions, I would say. So if you look at the OpenAI GIM environments or other kind of RL-focused environments, a lot of them are not geared so much towards robotic systems, so like accurate like dynamics or accurate vision or perception in the loop. So I think that's something that I definitely want to see more of. And maybe one kind of way to get towards that is kind of augmented reality. So maybe like hardware in the loop simulation. So some portion of the benchmarking environment could be actual hardware, but then maybe some other portion could be simulated. And I guess a couple of other panelists mentioned getting realistic simulations of humans. And I think if you have maybe augmented reality benchmarking environments, then you could imagine, for example, your robot is operating in simulation, but then there are like humans in the environment who are whose like motions are being kind of played in the simulation environment. I think another point that's maybe slightly technical, but I think is important in terms of adoption of benchmarks is having some kind of optimal or like ground truth level of performance, or like oracle performance. So if we think about image recognition, for example, then like a natural kind of comparator for machine learning algorithms is how well does a human do. Same thing with video games. So I guess like Dota or like other video game benchmarks, we can like compare our machine learning algorithms with how well a human does. So I think some kind of like oracle performance, right? Or here's like a really good benchmark to compare against. That's something that we're missing. So I guess as another example, recently over the last couple of years, there's been an interest in LQR problems, so linear quadratic regulator problems, specifically in the kind of controls and RL community, thinking about that as a benchmark. And I think one of the reasons that is the case is because we can calculate what the optimal, like what the best possible solution is. I think LQR, of course, is restricted, but I feel like that feature that you can have a bound on the best you can do kind of acts as a motivator. And that's something that I'd like to see as well in other benchmarks.
Great. And one very brief follow-up question. If you want to have this optimal, the optimal solution, that is definitely something you could do in simulation, right? Where you basically give the optimal solution the full knowledge about the dynamics, but the learner has only partial knowledge. So where do you stand on this topic, simulation benchmarks versus experimental ones?
Yeah, I feel like both have a role. I mean, I think ultimately I agree that we want benchmarks that are kind of hardware focused, but I think a lot of things could be done in simulation, and we shouldn't throw that away. Like, I think we should try to evaluate the things we can in simulation, but then ultimately maybe trust what we're seeing on actual like hardware platforms.
Okay.
If I can add to this, I think there's an interesting path that can take us all the way from simulation to the real world, including sort of human intervention and more realism. It's the path of going through teleoperation of robots and using VR as a way of abstracting essentially the setting. A lot of the benchmarks that we work on exist both in simulation in the real world with various degrees of fidelity, but then to what Annie was just saying in terms of having an oracle, we can also teleoperate every robot we have in simulation and actually evaluate, is the task feasible? Is it safe? Is it something that human can do? And also enables us to collect data so that ultimately we can turn that into autonomous behaviors. And I think that smooth path between fully teleoperated in simulation towards a real-world teleoperated, or introducing autonomy at various points there can really help sort of bring those benchmarks to a level where we trust them. They're actually reflective of reality, but they're also scalable and enable us to explore all the safety issues in a way that, not all, but most of the safety issues in a way that is safe and controlled and measurable.
Yeah, this is a great point. This has been something I've definitely been interested in. Like, how can we, if the robot would at least know when it doesn't know, then it could ping a human to kind of show it what to do at least once. Yeah, that's a really good point. And I think, Byron, you wanted to add something?
Yeah, so just a quick follow-up comment on simulation and real-world benchmarks and these sorts of things. So it just seems to me that simulation is a critical part of this pathway, this development pathway, basically, right? So if I come up with a good idea for an algorithm, what's the first thing I do? Like, obviously, like the first thing I do is I try it out in a simple problem in a simulator, and I try to figure out, okay, like, is this idea sort of even feasible? Is it like, something which is promising or not? That might be enough to publish a paper, right? So I think that like using simulation and validating things in simulation seems very reasonable to me. But then if we're talking about like something working on a robotic system, you must go beyond that. And so, the kind of pathway, again, it seems to me is like, come up with a good idea, test it in simulation, test it in offline data. That offline data, you could potentially collect it via teleoperation. You could get it from previous autonomous runs, and then implement the algorithm in the real system and see how the entire system works in the real world on a real world benchmark. And so I guess, like, in my view, simulation is something which is intermediate on a path towards real world deployment, and is, it's reasonable to be benchmarking things that way. But at the end of the day, sort of real world success is going to be king, because you don't know what you haven't thought of. You don't necessarily know precisely where the simulator is going to break down. So yeah,
Great.
So that's just my kind of thought on it.
Great. I think we'll finish off, the time is running out, with two very brief questions, and maybe you can just keep your answers also brief. I think one we have from the audience. SiQi, maybe do you want to go ahead and ask this one?
Yeah, so we have one question from Frick. Do you think it's better to have fixed systems and varying tasks, or fixed tasks and varying systems for benchmarking? Maybe we can start with Vincent.
Yeah, a lot of what we study is about task generalization. So we don't know the task at training time. We only know the task when we evaluate the system. So for us, it's more on the fixed system and then the diversity of tasks, but even unknown tasks is really the measure of success for the things that we do.
Okay. Annie, do you want to add?
Yeah, I would say, I think something similar to Vincent. So thinking about generalization to new environments, like that's something that we've been thinking a fair bit about in my group. And I guess you could think about like the task being encompassed by the environment as well. So yeah, I think that sort of generalization seems like a key to me.
So I agree with the other panelists, but I also just want to say that sort of really interesting tasks are ones that we don't know how to complete or don't know how to solve. And so in some sense, you could imagine having fixed tasks that, any sort of even partial solution becomes interesting and becomes sort of the benchmark for, all additional ones. And I guess I'm thinking of like the grand challenge, right? Where in the first run, no one completed the task or even came close. And part of the issue there was the system and the environment, and just like how difficult the task was. The next time, many teams completed the challenge, and then it was just who could do it fastest. So there's, in that sense, something like a fixed task, which I think was a very valuable benchmark, and I like that sort of thing as well.
Yep. Thank you. So I guess like we would have either task-centered or platform-centered also, but depending on what we ultimately want to achieve. So task-driven more of the algorithm designs and innovative solutions, but ultimately if we move to transition to a particular application, we eventually get down to more platform-dependent benchmarking.
Yeah, maybe we'll finish off with one quick question. And I'm interested in your thoughts around, what convinces people to actually work on benchmarks that have been designed? Like, how can we make sure that a benchmark is actually widely adopted? And some, that were very successful is, of course, the DARPA ones. There was a lot of money, and these tasks seemed like super exciting and challenging and almost impossible, right? The self-driving one, for example. I guess the racing example from Byron goes into this similar direction. It's exciting. It's easy to kind of compete. So I'm wondering, just one feature of a benchmark that would get you excited to work on it. And maybe we'll finish with this. And we'll start with Byron, and then Vincent and Ani.
Well, just to quickly reiterate, I mean, I like challenges where it's not clear how to, solve the problem. So like I like a race which is so difficult, or through such a difficult environment, or the task has requirements which are so difficult that we just don't know how to do it. So that's one feature that I really like. Another thing, just kind of a follow-up from earlier as well, I'm thinking about how to get tasks that people from different locations, different places are able to compete. Like, one thing to think about, especially for like a race or competition, is you can kind of have a course, right? So for example, someone who's the best at a marathon in the Netherlands is not necessarily going to be the best at a marathon in Colorado, like in the mountains. Someone who's the best tennis player on grass isn't necessarily the best tennis player on clay. And so, you could say, I was able to complete this task at my sort of like home course or with my home setup. Someone else can have something which is slightly different, and at some point you could compare on each other's. And so this sort of idea of like proposing and then allowing other people to compete against your solution at a particular task seems also valuable to me.
I think we have this challenge in robotics in general of how do we make tasks exciting, mostly because a lot of the very mundane things are extremely hard, and compared to some of the things that may be more flashy, like racing drones around, that looks like a lot of fun, but at the end of the day, it's free space motion compared to the grasping tasks that you feel like you would be able to do very easily, but are actually very hard. So I think there's a very clear challenge there. How do we make the mundane very exciting and very entertaining and very something that people value and reward? I don't have a solution for this, but I think that's a problem that we have robotics-wide in terms of making sure that people really sort of value and understand what's difficult and why it's exciting, and why some of the problems are more interesting than others, and in a way that doesn't sacrifice scientific integrity. So I don't have any good answer, but I want to flash that this is actually a really, really important problem for us to solve.
Yeah, I agree. Ani.
Yeah, I think something that seems important to me is benchmarks that allow different groups to kind of apply their approaches, maybe with some of the assumptions that they make, but ultimately still like build towards like a more general solution. And I think that seems like something that might drive adoption. So at least initially, people can assume like perfect state estimation or assume like fully actuated dynamics, but ultimately there's some like pathway towards like relaxing those assumptions and getting towards some like exciting demonstrations like some of the other panelists mentioned.
Thank you. Thank you, everyone. This was such an exciting panel discussion. I think we learned a lot about where the open areas are for the next benchmarks. We'll jump right into the next part, given the time. So we'll have very brief concluding remarks, and we'll point you to the panel discussion, the social event again. Yep, go ahead.
Wonderful. Thank you, everyone. Thank you, Angela, for hosting this. And thank you, Byron, Ani, and Vincent for wonderful insights. I think a good point of conclusion is very much like what Byron said, that probably we will not have a single algorithm that dominate, and we will live in the era of Nadal, Federer, and Djokovic. So for people who are new to the area of safety, the organizers, we have created an introductory tutorial for you. This is about an hour and a half of material so that you can quickly get up to speed on ideas in model-driven approaches, data-driven approaches, and ideas in combined approaches for safety. This is by no means supposed to be an exhaustive tutorial, but this is definitely supposed to be a quick enough tutorial for you to understand what is the latest and what sort of big picture ideas are going on in the field. If that is too much, if there is one thing that you take away from this workshop, please let it be this. Ideas in safety can be thought of along two dimensions. One, how much you know about the problem, and two, how strict of a guarantee do you need. A lot of the work that has been done so far has been operating in known dynamics, very strict guarantees, whether it's industrial robots or airplanes. On the other hand, we can have slightly more easier constraints and less sort of generalized dynamics that we have thought of in areas such as service robotics. We can go to slightly more complex domains, such as, let's say, robots driving on street delivering groceries. And really what we really want to get to is ideas where we can have true autonomy, where either it's autonomous driving or surgical robots, where both the world is general and we have hard and strict satisfaction safety requirements. With that, we hope many of you would find this exciting and would contribute to the material and keep the conversation going. Once again, we'd like to thank all of you for attending. For those of you who joined us late, feel free to attend the social event. The link to social is available on the workshop website, and the password is IROS 2021. Do consider submitting some of your work to our follow-up workshop on deployable decision-making at NeurIPS later this year. There's a lot of these resources available at the common page that we have put together. And finally, there's also an invited session on learning-based control at CDC later this year as well. Thank you all once again, and hope to see you all in the social.